Okay, I guess it has been a while since I last saw you 2 weeks ago. So let me just remind you, like the last thing I mentioned, and then today we'll talk talking more about the connection of all of these, like with symplectic geometry and some linear algebra. So like the last thing I told you about last time is that if you had like something like this harmonic oscillator, which is just a spring, like the Hooke's law. Okay, so that was a Hamiltonian, and then there you like the Hamilton's equations were the derivative of x with respect to t is a partial derivative of h with respect to p, and then the derivative of p with respect to t is minus the partial derivative of h with respect to x. Okay, so that's you know that is what you get. But if you remember, like the solutions were circles actually because of like the conventions that I use for the constants. So like you could have tried to study this problem using other coordinates. That's like the natural thing to do. Like you would do it all the time, like in calculus, right? So for example, if you had used the first change of variables, which would have been natural, it's kind of like switching to like polar, right? So you would have tried something like r equals root of x squared plus b squared, and theta, right? Like the arctangent of p over x, right? Because here, like if you draw the phase space, x is kind of like the horizontal coordinate and p the vertical one, right? And if you do the change of variables, you can then think of the Hamiltonian in terms of r and theta. Of course, like here, it doesn't really depend on theta, but like just in general, that's what you could have expected. So you just get r squared over 2, right? What's kind of what was interesting about this change of variables is that you cannot, using this change of variables, you can, like if you were just to write the Hamilton's equations with respect to these variables, like the analog of this, what do you get? You would get obtain the RDT would have been, I think actually it was like, let me see if I use the same order, like, let's see. I think, okay, no, this I think is fine. Right, if you just try to like naively apply the equations of motion like in this way, right, like pretending that it's the same, then like you would have obtained, okay, so this is fine, like the derivative of h with respect to theta is 0, and that's what you would expect because if you remember the solutions were circles, right, so the radius is not changing over time. So this is fine, right? But this one would have given you minus a negative, like gives you negative r, and we already knew that this is incorrect, right? Because if you remember, like the angular velocity, which would be the rate of change of theta with respect to time, was actually constant. It was -1 in all cases. So the issue with this is like this is kind of like of course it's like a change of variables, but it's not a change of variables that interacts nicely with the equations because you cannot just like compute the equations of motion like under these change of variables. So this is like this is what's wrong, right? So this change of variables does not, right? This one does not interact nicely with the equations. And then the other thing I mentioned is like, in this particular case, an analog of like, you could have done a slightly different change of variables, which was like for example, you could call I x squared plus b squared over 2, right? And theta, you can still let it be the same. And then the Hamiltonian in terms of I and theta is just I, right? There's nothing surprising about that. But then, like, this one does have the correct behavior, right? Like this, so this is kind of like what is R square, secretly it's R square over two, right? So this one does have the correct behavior in the sense that here, if you compute this stuff, you get zero. That also it still makes sense because it's kind of like the radius squared, basically. So like it is a constant of motion. And then the theta dt, now it's minus the partial derivative of h with respect to I, and that would have given you -1, and that's correct. That this is like what we know is the answer. Okay. So what I'm saying is that for this change of variables, you can just like compute the rates of change like using Hamilton's equations and you get the correct answer. So there is like a distinction between like this first change of variables and the other one, because in the second you can just like kind of like apply like formally the same equations of motions. Is that making sense? So the what we'll say is that, for example, going from xp to I theta is like a canonical transformation. So I'm about to give you like the definition for that. But like a canonical transformation is like a change of variables that allows you to compute the equations in the new coordinate system, basically. So it's like a kind of like a change of variables that preserves like the structure of the equations. Or map solutions to solutions. Like that's another way to think about it. So let me give you the, oh yeah, sorry.
What exactly would the interpretation of like the Hamiltonian of I data be?
Okay, so here is, well, in this case, like, like it is like usually, right, like in general, like the new coordinates do not always have such a straightforward physical meaning, right? Like it's more like a mathematical transformation. In this particular case, the theta, like it is like okay, like the theta is kind of like some sort of angle in the phase space, right? Like so if you draw the phase space, the theta is still recording like the angle of a point that's moving in phase space with respect to the x-axis. And then the I in this case, if you cheat a little bit, it happens to be like kind of like the energy, right? It does keep track of the of the total energy of the system. It just happened to be conserved, and that's why it didn't change over time. But in general, yeah, in general, you take like a more abstract approach, where you can you don't try to give like necessarily like physical meaning to like the new variables. It's similar to when you do like a double integral, like yeah, like you do like polar coordinates and things like that. But then like sometimes like when you're learning the Jacobian and like they just give you, well, suppose x and y is like are functions of u and v, right? And you no longer try to think about, oh, what is like u and v in this case, right? Like maybe sometimes there are hyperbolic coordinates, polar coordinates, but like there are many other changes of variables and it's not super obvious, like, what the meaning is. So like you kind of like give up a little bit. That's kind of what makes the like formalism powerful, right? Because you kind of give up a little bit on trying to like interpret what it all means. In this particular case, yes, like it's simple enough that you could try to give it a meaning, but in general, like you really don't try too much, if you know what I mean. It just suffices that there's like at least, I mean, most physical systems, like like that's kind of like the asymmetry, right? It's kind of like when you say like a vector space, right? Like if it's like an abstract vector space, there's no preferred basis, right? Like as a vector space, there are tons of bases. Like then it can be in particular applications or like things like that, where like the vector space, like it is more natural to choose a given basis for that vector space, right? But the vector space itself, like as an abstract entity, does not really have a preference. So it's kind of similar in this sense. Like, there are tons of like different coordinate systems you can give on phase space, and there may be like a few that are kind of preferred in the sense that they make more sense for us, but they're not necessarily like preferred like from a mathematical point of view, if you know what I mean. So it's kind of like an analogy of that sort. In fact, like what will do in a second is consider like I'll do today kind of like the linear algebra part. So we'll consider like linear transformations of coordinates. So we're going to consider things like, something like this, right? So you're just taking like a linear combination of x and p. That doesn't even have like a lot of physical meaning per se necessarily, unless you tell me a little bit more about what these constants are, right? So you're just defining it, but mathematically it's totally fine, right? Like, so that's kind of where we're going at, if that sounds good. No, but that's like in general, like more advanced treatments, you just say, well, the phase space is kind of like a manifold, if you know what that is, and then a manifold is supposed to have like many coordinate systems, and et cetera, et cetera. But in particular cases, then yeah, you may want to, connect this to reality, so you do want to like maybe think about certain coordinates. But in general, or like this level of generality, like it's not too important to try to see what this all means. But yeah, so let me. Let me give you a definition of um, like what a canonical transformation is. So again, like for now, just to make things like more like digestible in terms like the notation, I'll just assume that everything has like there's only like a coordinate for position and a coordinate for momentum. So really, for now, think of the phase space as being R2, just for like to make our lives easier or simplicity. In terms of like notation, like you'll see the PDF of problems, I'll add like the generalizations of all this, and it's essentially the same idea. You just keep track of more like indices. So let's call it okay, so let's call it add P for a phase space. Okay, so this is like the phase space is like R2 essentially. Okay. And you can think of like the Hamiltonian as like a function of like a real value function here. But so like if you thought about it as like R2, let's say, well, you have like coordinates x and p, okay? And again, like here, like if you have like the Hamiltonian in terms of x and p, you would say that like, the Hamilton's equations are like the things that I have been writing all along, right? So I have written this a couple of times. And again, like the solutions to these equations, because it's like a system of variables, it's just like a curve here. So this is like a potential solution to the equations. But again, like you could make like a change of variables. Okay, so now you make a change of variables. Okay, I'll just do it this way. I'll write it, yeah, like so now you think, well, maybe x and p are also are function, like, can be written in terms of new variables x prime and y and p prime. So like I'll just like then maybe let's say like maybe x prime is here and p prime is here. I don't know, right? I'll try to put it like I'm putting it in this way because like for today I'm doing it more like from the linear algebra perspective. So it will be kind of like an affine transformation. Like it would just like you just maybe like a rotation or like a contraction somehow, but so you think about x as a function of x prime and p prime, and p as a function of x prime and p prime. Okay, so in general, if you have used notations like this is how you would write it, like in a less mathematical notation, right? Like that you think of x as depending on x prime and p prime, and e depends on x prime and p prime. So here, like, you want to think of like this change of variables as being good. So, you think like of f f and g like as being like invertible changes of invertible functions and differentiable, etc., etc. So like you don't have to worry about none of those issues. And in fact, like this change of variables, like again, like not to get into too many technicalities, it doesn't need to be like globally defined. You can think about this like as making a change of variables just like in open set, if you have seen that like of the phase space, right? Which is what happens like when you switch from Cartesian to polar, because that's not even well defined everywhere. At least it fails at the origin, right? So like it just imagine like you choose like a region of R2 or you're making the change of variables, because it's a completely local thing. So um, okay, so x prime, p prime are the new variables, and you say that this is like a canonical transformation. Okay, so this is like a canonical transformation. If what happens, well, the stuff that I have been mentioning before, that you can't, like, you could think about, again, there are a couple of interpretations of doing this, like, but the idea is like X and P are, for a particular solution, X and P change over time. So, because everything is invertible, like X prime and P prime would change over time, etc. So the idea is like for a canonical transformation, you could just like find the rates of change of X prime and P prime in the naive way, meaning taking the derivatives, the partial derivatives in the same way. So what you want is that the derivative of X prime with respect to time is a partial derivative of H. I'll say what H prime here is. Where H prime is just like the Hamiltonian regarded as a function of X prime and P prime. So H. So the Hamiltonian inference. So you could write it H as well, like depends on how much abusive notation you want to make. So in other words, like, the Hamilton's equations like just work exactly the same in this new, with respect to these new coordinates. Is that okay? Making sense? So what I wanted to do today is kind of like solve this problem for like the case of a linear transformation. That like already gives you like a lot of interesting geometry and algebra that's going on. So it's kind of nice to work it out explicitly in that case, because it does give you a good sense for what's happening. And that's how actually we get into the symplectic geometry part of of this conversation. So, oh yeah, sorry.
When we're actually checking whether the canonical transformation conditions are satisfied, what exactly do we check to verify that these equations hold? Like, or do we need to have some sort of model in mind?
Oh no, so that's a cool thing. Like you'll see like an algebraic condition just pops out. Like once we'll start working it out again for the first in the linear case, and you'll see it's completely like, I mean, once you have like the actual change of variables, it will be completely clear whether or not it's canonical from this condition that's about to appear. So no, that's like, in a sense that you don't have to like, kind of like a lot of things that you may be worried about completely disappear, and like you don't even have to understand like what the solutions are or anything like that. It only depends on what's called like the symplectic form, which hasn't like appeared in what so far what I have said, but it really like it boils down to like a very concrete thing. Like, and so that's what makes it like a useful thing, because like otherwise, like what's the point? You know what I mean? So, and again, in the linear algebra, in the linear case, which is what I'll do today, you'll see like super like clear what it is. Like it's very nice to, I mean, really, like if you do things for 2x2 matrices, it's again like almost everything like else works in linear algebra just fine. So let's just start there, because again, like it's just easier to have the notation. It's just tedious of a notation, and like everything can be like checked like very quickly. So are there any other questions before like we go into that? So let me Yeah, so we only need like matrix multiplication and the chain rule for multivariable to see what this should be. So again, yeah, let's start with the linear case. So I'm going to like by that I just mean that I want to think of x as ax prime plus b prime and p as cx prime plus dp prime. Okay, so the change of variables is just linear in the in x prime p prime, or if you prefer, like obviously, which is how I'll write it in matrix notation, that this is a b c d x prime p prime, right? So the way the variables are related is like just a linear matrix by a matrix, and so we'll even think of a b c d as like being actual constants, like just like constants. They're not functions of like they don't change from point to point in space. That's like really like the most basic thing that you could do, and that already gives you like some interesting stuff. So because because we want to think of this as a good change of variables, like it should be invertible. So like the only condition I'll impose on the matrix for now is that the determinant is non-zero. So you can either think of xp in terms of x prime p prime or x prime p prime in terms of xp, right? So let me call this matrix S. I'm calling this matrix S for symplectic. So which will appear later on. I mean, then the definition will be more clear, like in a bit. So here, like the only condition for now. The determinant of S is non-zero. Okay, so that is like a good change of variables. Okay, and so then we just need to start computing things again using the change of variables rule. So if you remember, like you could think you can find that there like the Hamiltonian originally depends on x and p, but because of the change of variables, you can also think about it as a function of x prime and p prime. And so like they're like the chain rule tells you how that happens, right? Like I can even put, if you like, the diagram here. Right, something like that. So like the derivative of h with respect to x prime, the derivative of h with respect to x, and the derivative of x with respect to x prime, plus the derivative of h with respect to p, right, times the derivative of p with respect to x prime. Right, and because like the changes, because this is like a linear change of variables, I mean, it just like gives you something easy to compute. And then this the derivative here is c prime. And the same code for the other one, right? Like it's the same, but with p prime instead. And non-surprisingly, it gives you basically this same structure, but with the other constants. Right? And again, like it's always better to write it in matrix notation, right? So like if you like what this is saying, like if you prefer to write it this way, which is convenience anytime. It transforms, like it is almost, it's with the transpose of the matrix, right? That they're related, like this is S transpose. So it's ACBD times the derivative of H with respect to X times the derivative of H with respect to P. Right. So, I mean, this is like, if you have ever done tensor analysis, it's like the type of thing that you think about all the time. Like so like if the variables transform with S, right, like the gradients, transformed with ST, the transpose of the matrix, and that's like has to do with whether like you want to think of a vector as contravariant or covariant and things of that sort. So so if you want like even like to write this in like a more succinct notation, you could say that the gradient of H with respect to the variables x prime p prime is S transpose times the gradient of H with respect to the variables x comma p. I mean, just like to summarize that in that way. So far, so good. Questions about this? And we're almost done. Like now we just have to write all of this down. So what was so like I don't know if you remember, there was this matrix J that I had written before, like which was 0, 1, -1, 0. The nice thing about that matrix J is that you could write the Hamilton's equations in a nice way because it was just taking the gradient and rotated by 90 degrees. If you remember, like how you know how you could write the equations here. So like they like and then the matrix way to write the Hamilton's equations were like J times the gradient. Right, that's like how you would write it down. So if the transformation is canonical, the same will happen here, but everything is primed, right? So it would be the x prime dt, dp prime dt, J is still J, that's just like a constant matrix, and then you just take the gradient here with respect to x prime, p prime. So because this is supposed to be canonical, since the transformation is canonical, it is canonical. What you should have is that dx prime dt, dp prime dt should be the same as J times the gradient of H with respect to x prime p prime. Okay, so you see like formally, that's the point of a canonical transformation. You just prime everywhere in the equation and it looks the same, right? Like that's what it's kind of like what physicists call like a covariant, like, you know, it just like get the same form of the equation in the new coordinate system. So we already know what this part is, right? So this just ends up being J times this gradient, but this is what I just found for you. So it just gives you ST, like, you know, transpose of the matrix times the gradient of H with respect to xp. And again, and actually this one is easier to find because, you know, you can kind of extract it from here. Like, you know, if you multiply both sides by the inverse, right, you get that, let me put it here. You know, if you multiply both sides by the inverse of this matrix, you get x inverse times xp equals x prime p prime, right? So like the time you just differentiate both sides with respect to time, and so you'll get you know, you'll get S inverse times you know, the xdt dpt. Right, so like what I'm saying is that yeah, if you take the derivative with respect to time, both sides, that's how you get what the x prime. Because again, like the matrix doesn't depend on any, like it's like actual constant, right? Like the letters are actual constants. They don't depend on the position in phase space. They don't depend on time or anything. So like the derivative with respect to time just goes through, ignores the matrix completely. Okay, and so far so good. We're almost done. So we have S inverse here. But what is this vector? I mean, this vector, like we're assuming that you had like a solution to Hamilton's equation. So it's still J times the gradient with respect to the original variables. Okay. So we're almost there. That's really cool. So hey, like if you haven't ever seen this like before, like this, I have a nice calculation. I mean, these are all like square matrices, invertible square matrix is invertible, this is like just a vector, but it's not the same vector on both sides, right? So essentially, what you would, it's just like for this to hold, like what suffices, like, like just forget about the vector. What you need is S inverse J to be J as transpose. So like, for the transformation to be canonical, if you're trying to find like a condition that would like that makes it kind of like, like not to get into necessary versus sufficient conditions. If you just want something that to guarantee that works all the time, just forget about this side and just try to find like a matrix. So let's just ask. So to make that hold automatically, make this hold. Just ask for S inverse J to be the same as J as transpose. Okay, and just to make this like looking the way that's traditionally written as like just say that J has to be S times J times S transpose. And this, so the matrix for it to be canonical has to be one, where if you do S times J times S transpose, you get J back. And that is what's going to be a symplectic matrix. Okay, so this is like the condition that we are after. And I'm about to explicitly work it out so that you see what it gives you in this 2x2 case. But it's like the thing is like this is actually what happens for any size of matrix. Like it's the same analysis, it's just like more tedious. So for any, like could be 4x4, 8x8, like all of these have to be even matrices. But regardless of the size, this is like the condition. And then like the specific, like in the 2x2 case, it becomes even more explicit. And that's what I'm about to tell you in a moment. So we're looking at matrices that satisfy this condition. 2x2 matrices that satisfy this condition. That making sense? So far, so good. Questions about this? Oh yeah.
Wait, so you mentioned before like some big geometries about like even dimensions.
Right.
So like to find this, like you said, it's true for like, let's say like a 3x3, but like, does that have like any meaning, or do we only want like even?
No, like so the thing is like okay, so it depends on how you set it up, but these you can like I'll try to write it on the problem so that it's kind of like you can show that this only works in the even size matrices. So because in the sense of like the thing is like you would have to think like if it's 3x3 for example, what would you want the J to be, right? Like because like like for example in the 4x, maybe I should say what J is kind of like in 4x4, 6x6, things like that. So the idea is like the idea of J is always to be 0, identity minus identity 0, or these are like now n by n matrices. Right? So like, in the 2x2 case, like it's just like 0, 1, minus 1, 0. But in the 4x4 case, it would be like something like what? 0, 0, 0, 0, 1, 0, 0, 1. Well, I guess minus 1, 0, minus 1, 0, 0, 0, 0, right? This would be like the 4x4 J. So like, if you try to like define like a J in the odd case, it's kind of like weird in the sense like, like you have like an asymmetry, like in how you like put like, how do you distribute the ones like negative ones, if that makes sense, like outside the diagonal. Of course, like there are other ways to, again, like it really depends on how you want to approach the subject. But I'll put it like more like, yeah, you can show, like, you can show, like, it depends, like, you want to say, well, maybe the J needs to satisfy certain properties, and then you show that a J that satisfies those properties can only be of even size. That's the easiest way to say it. Kind of like because, like, like the important thing about J is that it squares to minus the identity. So it's kind of like an analog of I, right? And then you can show like that a square matrix whose squares to minus the identity can only be of even size. So it's like you play with the eigenvalues. I mean, it's like a game with the eigenvalues. I'll write it down on the PDF if you want to see like the steps. It's like an easy proof, but it's still kind of nice to do it, So But yeah, thanks.
Is it something like the eigenvalues or the MPs are the only one where I is?
Yeah, it's kind of, don't, there's like an, there was some symmetry between the eigenvalues or something like that, and that's how you, it's like an easy proof, like but yeah, like, or something about the kernel, like, yeah, the matrix, but yeah, no, it's not too bad to show, it, like, it's a cute proof, I'll add it to the PDF if someone wants to go through it, but I'm just saying, like, yeah, you could maybe say, like abstractly, like the J, maybe like the only thing you care about is that it corresponds to the identity, but then you just show that that can only happen on even dimensional vector spaces. So that's kind of saying like they're only like that's actually what you would call like a complex structure in a vector space, a matrix whose square is minus the identity. And then you say that what that shows is like only on even dimensional vector spaces, they're complex structures. Yeah. But yeah, no, it's not a it's an easy proof, but it's just like depends on how you set it up to see it more easily. But yeah, I think it's just like in terms of the, you just play a little bit with the eigenvalues and like some symmetries that, you know, that would come in pairs or something like that sort, and then you're done. But cool. So, okay, so far so good. Any other questions? Okay, so now you'll see why we're getting to the, yeah, so for the approach of taking it is kind of course, granted that it's all even dimensional because I started with the phase space that is always like even because it was like a system, you know, if you start from Newton's equations, they're second order in time. So once you make them into first order equations, you kind of double them always automatically. So that's why this always like even from that physical perspective. But yeah, they're like mathematical roads that you can take where like you also show that's even from like mathematical reasons. So that let's just work this out explicitly in the 2x2 case. It's kind of like nice to see how this looks like. That's why I like 2x2 matrices because everything can be done like super quickly. So you get 0, 1, minus 1, 0. That's the left-hand side. The matrix S was A, B, C, D, right? J is 0, 1, negative 1, 0. And the matrix, and I'll tell you other ways to think about this like in a moment. So, and the transpose is A, B, C, D, right? So you just get that. And so again, like it's an easy multiplication. We can do it. So when you do this, you get negative P, and then you can do this one and you get A, and then you do this one, you get minus D, and then you do this one and you get C. Okay, so if I make any mistakes, just let me know because it's. So these two cancel, perfect. And then you get minus BC plus AD, and then the other one is going to be minus AD plus BC, and the other one is 0. Okay. So of course, like the only one that's in it, I mean, this all works well, like right now, like this one is minus the opposite of the other one. So there's really only one interesting equation, right? Which is that 1 equals AD minus BC, right? And so of course, like that's something you recognize, I think, right? So what is saying that the determinant of the matrix has to be 1, right? So in the 2x2 case, the canonical transformations are exactly the determinant 1 matrices, at least in like for linear linear changes of variables. So determinant, remember we did start with determinant of S being non-zero, so that like the change of variables could be invertible, which is like a natural thing to ask, so that's not too bad. But in the 2x2 case, like S is in, oh, by the way, I still haven't given a name for this thing. I'll call them, you can call this matrix canonical or symplectic, you'll see why. So we'll say that S is canonical. Or symplectic if then whenever determinant of 1 is determinant of the matrix is 1. There are more conditions in like 4x4, like 8x8 case. Like it's always true that they must have determinant 1, but there are more things that you have to add on top of that. But in the 2x2 case, the nice thing is that exactly just that, like the only thing that you need to ask. So S is canonical, symplectic, precisely when the determinant of S equals 1. Is that making sense? And what's a nice thing about the matrices with determinant 1? Well, I got a couple of say, I mean, there are a bunch of things to say, but let me start saying like, first, like, more algebraic things, right? Like you remember like these properties of the determinant of A times B equals the determinant of A times the determinant of B, right? That's a thing that you know, and the determinant of the inverse, I mean, obviously for A invertible is one of the determinant of A, right? So what that means is that if the product of two canonical matrices will be canonical, right? Because 1 by 1 is 1. And that the inverse of a canonical matrix is canonical, or like a symplectic matrix. So if S1, S2, or like I will just keep them calling them symplectic because of the name I will use, because like now I'm getting to the like more math part. So what this is saying is that if S1, S2 are symplectic, which again in this case just means that the determinant is 1, then S1 S times S2 is symplectic. And if S is symplectic, then the inverse is symplectic. And inverse is symplectic. And it's easy to check that the identity is symplectic, right? Because it has determinant 1. Plus also identity is symplectic. So these form a group, right? If you have seen the definition of a group. So this is called the symplectic group. So these matrices form a group. Okay. So far, so good. So I'll give you a little bit more of the group structure that this has, because it's what people call a Lie group, meaning that it also has like a space, like topology, or like it is like a hypersurface of R4, for example, in this particular case. We'll see that in a second. But before that, let me just do like a more like linear algebra comparison of what's going on. So okay, so then I'll keep this condition written up top, right? So that's again, the condition for being symplectic in general is that, but in the 2 by 2 case, it just reduces to determinant being 1. So here's like a more of an analogy way to think about what we're doing. So here's like an analogy. So for vectors in Rn, right? You can define the dot product, and you can think about it as a bilinear form, right? And you can take the dot product. Right, this gives you like a bilinear form because, like, if you think about them as columns, right? So this would be like n by 1 matrix, and then this becomes a 1 by n matrix. So you get something 1 by 1, which happens to be the dot product, right? So the dot product is bilinear, and then when you ask, what are the matrix, like the invertible matrices that preserve the dot product, right? So if you change the vector u to something like s times u, and the vector v. Oops, let me just put in the arrows. To S times V, right? What's the dot product for these new vectors? Well, you just get, you have to transpose the first one. So when you transpose the first one, you change the order of the factors. So you get something like this. And SB is just SB here, right? So in order to preserve the dot product, you need S transpose S to be the identity, which is like the definition of an orthogonal matrix, right? So to preserve the dot product, you need this to be identity. So you can think of the orthogonal matrices as being those that preserve the metric. This is like the other name for that, the metric. The symplectic matrices kind of rise in a similar way. So there's like a bilinear form you can define. And this is where the famous symplectic form appears. So there's a thing called the symplectic form. Here's the symplectic form. We told you the name omega because that's usually how it's written down. So it's going to be exactly the same definition, but I'll just sandwich a J in between. So it's going to be U transpose, but nothing crazy, like just put the J in the middle. Okay. And then, so it's still like a bilinear form. It's actually going to be skewed, there's certain things you can check. It's going to be like, if you change the order of factors, you get a minus sign, for example. I'll give you like an explicit formula in a second, so it's more easy to see. But for now, you somehow just define this for whatever reason, and then again, you can ask the same that, oh, what if you change U into S times U and B into S times B? What happens with like the expression of omega here? You get omega of SU, omega SB. Again, like it becomes the same, like you get U transpose, S transpose, J SB, right? So if you want this to agree, if you want this to be exactly the same value as omega of UB, right? If you want these two things to be the same, you need this to be sorry, there's no more J here, S here. Right, so for these two quantities to agree, you need this to happen, so that forces these two things to agree. So you need S transpose J S to be the same as J. Okay, and that's almost like, it's almost exactly the same condition as the one that you see here. It's not quite the same. That's saying that S transpose would be symplectic, right? Like under this definition. So S transpose is symplectic. But it's easy. I mean, in the 2 by 2 case, it's not a problem because the determinant of A is the same as the transpose. So like if S transpose is symplectic, S will be symplectic. And in general, you can also show the same, that if like a matrix is symplectic, its transpose is as well. But then this forces S to be symplectic. So regardless of how you see it, like what I'm trying to say is that like the matrices that preserve these bilinear form are precisely the symplectic matrices, if that makes sense. So it is kind of like what were these matrices, the orthogonal ones were like kind of rotate, I mean, as if they have determinant one, they're rotations, right? Like the orthogonal matrices. Reflections are also involved if you allow the determinant to be -1. So the matrices that preserve the dot product. How much time do I have left? Like 30 minutes maybe, or okay. So the matrices that preserve the dot product were like rotations, reflections, like orthogonal matrices. The matrices that preserve this thing happen to be exactly the symplectic matrices. Okay, is that making sense? And in fact, like you can give like a more explicit representation for what this is. Let's just work it out. It's kind of nice to have like a more concrete. So like what I'm trying to say, like maybe I should write it as an analogy. So orthogonal is to the dot product, G as symplectic is to this omega thing, as symplectic is to omega. So like the symplectic matrices play the role of the things that preserve the omega bilinear form in the same way in which orthogonal matrices preserve the dot product. Okay. Now it's better to have maybe a more concrete idea of what this actually gives you. So to do that, again, let me just write it down in the 2 by 2 case because that's where we're focusing for now. If you write U as U1, U2, right, and B as V1, V2, what is omega of UV? Well, it's just U1, U2, 0, 1, -1, 0, V1, V2, right? And so again, this is not too bad to do. Like if you multiply you get minus U2, and then you get U1, right? Times E1, U2. And what does that give you? It gives you minus U2 V1 plus U1 V2. And what is that? That's the determinant of a 2 by 2 matrix, right? So right, like the determinant of this 2 by 2 matrix is precisely U1 V2 minus U1 V1. So omega really is just the determinant of the 2 by 2 matrix. More geometrically is the area of the parallelogram, right? Because if you have two vectors on R2, the determinant is a parallelogram up to a sign, right? So this is just, so what I'm saying is that really you had two vectors U and V. Right, and has some area. And this area is essentially plus or minus, like, because like in absolute value, it's plus minus omega of UV. So omega really just records like the area up with a sign, right? Because of orientation stuff. So like it's kind of like in the same way in which it works like in before. So this is more closely related. So the symplectic matrices are essentially the matrices that preserve areas of parallelograms, right? If you think about it. So as a symplectic, if it preserves the area of any possible parallelogram on the plane, if it preserves the area and the orientation because they have determinant one, so it doesn't mess up like which one comes before the other, like when you orient these things with the right-hand rule, for example, if you want to do it that way with the cross product. If it preserves like the area on orientation of all parallelograms on the plane. Okay, is that making sense? So that's why this is related. That's if you remember like the syllabus I had written. Well, symplectic geometry is kind of like the study of area in a sense. So this is where like at least in 2 by 2 case, like this is where the area comes in because secretly the in this particular case, like it does what you would call the symplectic form just happens to agree with like the area of the parallelogram, basically. And this is again all matches like this thing that I had told you 2 weeks ago about the Duville theorem that the idea is like a Hamiltonian system preserves the measure or the volume. So it's kind of like the linear algebra version of preserving the value of the size of a set is preserving the area of parallelograms because that's the only thing that you can really build in linear algebra, like parallelograms, parallelepipeds, things like that, of that sort, like, so like the linearized version of that is just saying, oh, you preserve areas of parallelograms, right? So it all, like in that sense, it all plays together really well. Is that okay? Is that making sense? Okay, so in the last stuff that I wanted to mention today is just I'll just tell you a little bit more about the structure of the symplectic matrices. So again, the symplectic matrices are the 2 by 2 matrices with determinant one, but they have like a geometry associated to them that would be useful later on to see, and it's also just nice to see in general. Like so, let me erase. So let me just write sim 2R. So this is going to refer, let's think about it for a set for now. So this consists, what is this set? It consists of the 2 by 2 matrices, right, of determinant one. So essentially the symplectic matrices because of what we have been talking about so far. So But I mean, there's like a more geometric way to think about it because, so this is like a subset of all 2x2 matrices, right? But the 2x2 matrices can be identified with R4, right? So if you have like a 2x2 matrix, so like this is just now like a random 2x2 matrix, you can put it in bijection with R4, right? Just by, I mean, it's not canonical, but you can just enter, write them like A, B, C, D, right? Like it's not, that gives you like, it's like some isomorphism, as vector spaces, for example. So if, but it's just like easier to think about it from R4 just to describe the geometry. So on R4, you can define the determinant matrix, right? So you, sorry, like the determinant function. So like you have like this determinant function that goes from R4 into R, right? It's real value. So you just take the vector A, B, C, D into like the determinant, right? Like A, D minus BC, right? And so the symplectic matrices are the level set for the determinant matrix of level set equals to 1, right? So this is like the inverse image of 1, right? Because we're looking at all the matrices with determinant. So far, so good. Is that making sense? So it is kind of like the analog of a level curve of a level surface, right? In Calc 3, right? It's just like in R4, so it's like a hypersurface, right? Because if you think about it, it's just AD minus BC. So like the way you had four variables, one equation. So essentially, like you kind of should be able to get rid of one of the variables, so you get something of dimension 3, right? So this is actually going to be like a 3-dimensional subset in a sense inside R4, like, and I'm going to describe that for you in a second. So how, what was like the way to, like, if you had like a level set in Calc 3, what would you do? Like the gradient would give you like the vector perpendicular to the level set, right? So what's the gradient of the determinant function? I mean, again, it's like if you think of this as x, y, z, w, right? Like those are like the coordinates now in R4. So the determinant is like the partial, it looks like a bit odd, but partial derivative of determinant with respect to A, partial derivative of determinant with respect to B, partial derivative of determinant with respect to C, and partial derivative of determinant with respect to D, right? And so the determinant is just A, and so like the derivative with respect to A just gives you D, the derivative with respect to B gives you minus C, the derivative with respect to C gives you minus B, and the derivative with respect to D gives you A. Right, so that is a vector that's normal. So like maybe I should start drawing like a picture, right? So I'm saying like I have like R4, and inside R4 sits the space or set of all the 2x2 determinant 1 matrices. So here's like the symplectic group. Right, and I just found like a normal vector at any point on the symplectic group, right? So the normal vector, let's call this n. So this is a normal vector, right? So if you have like a point A, B, C, D, let me represent it again as a matrix just to cheat a little bit. So if you have a matrix representing a point in this subset, then the normal vector is D minus C minus B A. And the idea is like this is like a nowhere vanishing normal vector, because, so this is nowhere vanishing. Because, right, what would need to happen for this to vanish, like all the coordinates have to be 0 literally, and then that would force the determinant to be 0. So it's nowhere vanishing for any point in the symplectic, for any symplectic matrix. Is that making sense? So in fact, this what it is called like it's an orientable hypersurface, right? Because if you remember something like the Mobius strip, the point of the Mobius strip is that you cannot find a nowhere vanishing normal vector field. So it is, and the fact that it's nowhere vanishing actually because of the, implicit function theorem or whatever, like it means it can be parametrized. And so it's like a hypersurface, it has 3 parameters, because like there's only one condition here. So it's really like a 3-dimensional thing. Like it's what you would call like a 3-dimensional manifold or hypersurface inside R4. So it will be like an orientable 3-dimensional hypermanifold. It's what people call like a liquid. So this is like so you end up finding because of this that this is like again, like if you haven't seen the terminology, it doesn't matter too much. but it ends up being like a pineapple and or so like or like a smooth hypersurface if you prefer like that terminology. Does that make sense? And then you know, just to start wrapping this up. So this gives you like what this is telling you is that you know, this set is not only a set, it has like more structure because it does look like some sort of hypersurface in 4 dimensions. And one thing that being a group, the point of being a group is that you have like a preferred element, which is the identity, right? Like the favorite element of any group is the identity. So you have, when you have the identity matrix here, right? So you have a normal vector associated to the identity, which again, that's kind of like a nice coincidence that like the normal vector to the identity just happens to be the itself, like if you look at it in terms of the entries, because D is 1 and A is 1 and the other two are 0. Okay, but the important thing is that if there is a tangent plane, that's like actually more like or tangent space. So there's a tangent space here. So there's a tangent hyperplane or a hyperplane, right? And there's a matrix, right? How it's another way to think about it? How it's another way to think about this hyperplane? Basically, what you draw is a bunch of curves passing through, you know, through the identity matrix, and then the hyperplane is built out of all the directions of all the possible curves. So if a vector is tangent, if a vector belongs to this hyperplane, it has to be perpendicular to the normal vector, right? So let's say that you have a matrix here. So let's say that you have like a vector, let me call it like a vector. Let's say x, y, z, w. Let's say that this vector represents a direction of the tangent hyperplane at the identity. And if I'm, well, yeah, obviously stop me if I'm saying things too fast. So let's say that, I'll call this A for using for y. So this is going to be a vector in that, you know, in the hyperplane of the identity matrix. So it has to be perpendicular to the normal vectors in the ordinary sense of the dot product has to be 0. Okay, so I mean, this is like an easy dot product to do because like the normal vector of the identity is just 1, 0, 0, 1. So you get x plus w equals 0, right? And if you the important thing is to reconvert this into matrices. You really want to think about this as a matrix. So what does x plus w equals 0 mean in the context of matrix that the trace is 0, right? So that means that a matrix A belongs to the hyperplane of the identity if the trace is 0. Of the identity if the trace is 0. If and only if, actually. I'll put it like this. Does that make sense? And again, I'll probably add some about it in the on the PDF of problems if someone wants to do it. This is like close on their commutators, right? Like this is like a Lie algebra. If you have seen this before, because if you have two matrices, right? If you have two matrices with trace 0, A1 and A2 with trace 0, what is the trace of the commutator? The trace of the commutator is a trace of A1, A2 minus A2, A1. I mean, but then that gives you something. I mean, that's just because, like, I guess, like the trace condition, like it has trace of AB is the same as trace of BA. So that gives you 0 again. So that means that if you have two matrices and you take their commutator, that's still like in the tangent hyperplane. So A1, the commutator is also in the tangent plane. And that's like, if you have ever seen like a Lie algebra is like the saying that this, like the tangent plane has like a Lie algebra. structure. Not that we need that so far for now. Okay, so this is what's called like a Lie algebra. Okay, that's not too important at the moment, but let me just tell you what's important at the moment, to remember from, this discussion, and that's what I'll finish with today. So, what's kind of nice to know. Let me just redraw this picture because now it became a little bit of a mess. So. Again, this is kind of R4. You have the space of symplectic matrices here. The identity belongs to this space. It has a tangent hyperplane, right? It has multiple direction vectors. Let's say that one of those vectors is A. So it's like a vector that is lies in the plane. So here was a normal vector. The reason why this is important is that there's another thing that you can do is that if you take what's cool about the Lie group stuff is that if you take vectors in this hyperplane, you can exponentiate them and get elements of the group. So every group, every element of the Lie group is actually an exponential of one of these. So let me just try to say what I mean by that. So you can let's just consider. So you have like a matrix A with the trace being equal to 0. Okay, so this is a 2x2 matrix, right? Of trace 0. Any 2x2 matrix, you can take the exponential of that matrix, right? So you can take e to the A. And let me just multiply it by time t. So it's kind of like, essentially, I'm just like exponentiating the matrix, but I'm also allowing for it to depend on on a parameter t. That's kind of convenient. You'll see later on. Essentially, that's also how like systems of the ODEs are solved, right? Like if the matrix of the system is constant, you can just exponentiate them. Okay, so this is a 2x2 matrix, right? And my claim is that that's a symplectic matrix. So the exponential of this matrix is symplectic. So my claim. If the trace of A equals 0, then for any t, for any number, for any t, a real number, e to the ta is a symplectic matrix. Okay, but let's think about why that is the case. So what's the condition for being symplectic in the 2x2 case? Just that its determinant is 1. Right, so I'm secretly saying is that if you exponentiate a matrix with trace 0, you get something of determinant 1. Right, so we need to check the determinant of s of t equals 1. So is that making sense? And now, anyone remembers, like, what's the determinant of the exponential of a matrix? There's like a formula for that. Look at the determinant of the exponential of a matrix. There is a way to find it. Anyone knows the answer? There's actually like a very cool way to remember it, because it's not super obvious how you get it. So let me tell you how you can get it. Like the easiest way to define the exponential is in the diagonalizable case. I mean, it is like a power series definition, right? Like, so there's really, you use like a power series to define it. But in the diagonalizable case, like A is diagonalizable, it's just Q, D, Q inverse, right? For some invertible matrix. And the exponential is like the most obvious thing you could take. Like e to the A is like Q, e to the D, Q inverse, right? So its determinant, right, would be the q's go away, so it's just the determinant of e to the d, right? But in the diagonal, in the diagonalized, for a diagonal matrix, the e to the d is just e to each eigenvalue, right? So this is just e to the sum of the eigenvalues. But what is the sum of the eigenvalues? The trace of a matrix. So this is just, this is so cool. So it's so elegant. So it's just like the trace of t times a. T is like, I mean, it's like just a number, so it doesn't have like that. So it's just a trace. But e to the zero, okay, so you get zero because it is trace, so e to the zero is still the identity, right? This works well. Of course, like this keeps working, even if it's not diagonalizable, but this is like the easiest way to remember the formula, Okay, that's very cool. So what that means is that, if you take, the way, there's like a useful way to think about elements in the symplectic group, which is just as exponentials of matrices in the tangent space of the identity. That's kind of like a story that more or less holds like in any Lie group. So the idea of like any Lie group is that it's like a space, so it has a tangent plane of the identity, and if you exponentiate the elements there, then you get like the elements of the group. This is more or less on the nose true when the matrix, like the group is represented by matrices. So there's like always like it's more like, you can put it like in more abstract terms. Otherwise, but it would be, it is a nice thing to have, because what will happen later, is that what will happen later is, this will once we get to quantum mechanics, like I'll tell you some about stuff. But in quantum mechanics, what will happen is that you will want to exponentiate. You want to take like an exponential of the Hamiltonian, basically. This will be like a Hermitian matrix, essentially. So like a symmetric matrix, if you haven't seen that name before. Like, so the Hamiltonian will become like a symmetric matrix in quantum mechanics, and then the exponential of the symmetric matrix will be a unitary matrix or an orthogonal matrix. So what that meant, like what that ends up happening is that, it's kind of like a vector. Like you have like a vector, which will be the wave function, which people call usually psi. So, and then the way the wave function evolves over time is by exponentiating the Hamiltonian. And so that is like an orthogonal transformation. So what that means is that the way in which like as the quantum state evolves is like kind of like a rotation in infinite dimensions. So it's kind of like an infinite dimensional rotation. So it's like a very cool story, but it's kind of like that. It's essentially like an infinite dimensional version of what we're doing now. So really you call them operators, not matrices, but I'm kind of like doing it just like sleight of hand, but it's it's still kind of like this is called like the Stone's theorem. But then like it's the exponential does become useful eventually, so that's why it was nice to at least bring some of it now. So like this is like more like cool. I mean, there are many cool things that happen already in 2x2 matrices if you think about it. There's like a lot of geometry, linear algebra involved, and it's just 2x2. So next time I'll tell you more about this. I actually have to, I'll tell you about the Poisson brackets because that's like a very important stuff. Because that really sets the stage for like what it means to quantize a system. So, but with like the stuff that we have discussed already, like it won't be that hard to describe that. Okay, so okay, let's finish here. That's a good place to start. So I'll add some more problems to the PDF if you want to just check some of those things out, like detail that I'm omitting. Questions before? Okay, cool. So let's meet next Wednesday. Keep talking about this.